It's not here.
Hey, you guys gonna take notes? Aren't you excited? Yay.
Your leg ain't broken. Stop. No, it's not.
So you guys will have a new equation today, assignment 14. In order to get through this, we have to learn some new stuff about logs. So I've got just a short list of like notey stuff, and then after that, of course, it's all examples. So we want to practice our skills. So there's going to be some new stuff coming down the pike today. Number one, some properties of logs that we haven't really discussed yet. And then number two, we're going to start seeing answers that don't work. So it's a kind of a whole big couple days of newness here. So those answers, remember, are called extraneous solutions. You've seen them before with absolute values. I think you saw them with radicals for sure. Those answers that when you plug stuff back in, they don't work, right? So you're going to be seeing that today as well. Yep. Number one, let's talk about just some basic properties of logs. So the first property of log, I decided this year not to spend several days on just talking about the properties of logs. Thought it would be better if we actually just use them to give this a shot instead of actually just quizzing you on explicitly using the properties for the sake of using them. We're going to use them for the sake of solving equations. So the first property says this: if you have the log of a, and by the way, for my notes today, that could be any base. This obviously is a base 10, but it could be base 4, base E, base 11. It doesn't matter. So if you have a log of something and you add to it another log of something, provided that the logarithms have the same base, then you can do something called condensing. And you condense those. Condensing, means to package tighter, like to bring it together, smaller package. And so if you have a log of A plus a log of B, you can condense it into the log of one thing, A times B. That's going to be a property that gets us through a lot of math problems. So that again is called, that act, you probably need to know this word just so that we can use it when we talk. That's called condense. You're condensing a logarithm at that point, or condensing two logarithms, I should say, into one. So for example, if I was going to write an example of that, I would say, like, if I had log base 4 of 5x, and I added to that another log base 4 of, say, 3. If I condensed those, I would condense into another log with a base of 4. And what would the argument of this log be? 15x. Very good. Right? Or if I had log base 19 of 3x minus 1, that quantity, and I added another log, also with a base of 19, of, we'll say, x. Then we'd have to use a base change formula, which we're not going to do. So all your bases will be the same. Good question. So if we were going to have you use these properties, so we're going to give you just same bases all over the place. So just know you can use these properties. So again, if I add two log base 19s together, I condense into a single log base 19. What would the argument of my new log be? Very good. 3x squared minus x. So you understand that if you multiply the argument of the first log by the argument of the second log, that's just basic distribution, 3x squared minus x. Okay. Any questions about that first property? All right. The second property works similarly. Probably won't need me to finish this for you. I'll see if you can figure this out. If I have a log, again, any base, it doesn't matter, with an argument of a, and I subtract a similar log. Again, same base, different argument. You guys want to guess this time how we condense? We divide. So we condense into a single logarithm with an argument of a divided by b. So again, for the sake of example, because by the way, again, that is, I'm going to say the word again, that verb, what we're doing there is called to condense. All right, so anytime you have two logarithms and you're able to, you generally would like to condense them into a single logarithm. So as an example of that, if I had log base 5 of 3x and I subtracted a log base 5 of 7, what would that condense into? I heard 3x over 7. It's not like I'm trying to ignore you, but I'm not going to take 3x over 7 as an answer. No, it involves 3x over 7, but that's not the answer. Thank you. Yes, it is log base 5 of 3x over 7. Please don't forget that when you condense two logs, you make another log. So that's not like a detail, right? We good on those two properties? All right, and then the last property that we're going to talk about today is I hope pretty common sensey. It says this. It says that if you have a log of a and it's equal to a log of b. You've seen these in geometry before. If-then statements. If this is true, comma, then this is true, right? We call them, I think, the hypothesis and the conclusion. So if this red box is true, if a log of something is equivalent or equal to a log of a different something, do you want to guess what has to be true? I don't know why. Yes, very good. Then A equals B. Super useful property. It's going to get you through probably more than half of the homework, or something like that, a lot. So the idea here is I can take a logarithmic equation and I can actually convert it into a regular equation by just acknowledging. And if you want, I mean, the proof of that, I hope, let me just give you a quick example as to why this would work the way it does. So like if I, and you've seen this before, I think, if I had like log base 4 of x, and I set that equal to log base 4 of, I don't know, let's do like 150. I mean, if you understand logarithms, then you understand that this one I'm underlining in green is a power of 4, right? It's what power of 4 would equal x. And then if on the right side, if you understand logs, then you know that this yellow one, again, is another power of 4. What power of 4 has to equal 150? But if someone's bold enough to put an equal sign in between them, the only way for those logarithms to equal each other is if the arguments themselves equal each other, because they're both powers of 4. So like if I had log base 4 of x equal to log base 4 of 150, I don't know what x is. Actually, I do. X has to equal 150. Can we agree with that? It's almost so obvious that it's maybe a bit difficult to understand at first, but that's the idea. If your logs equal each other, then the arguments of the logs have to equal each other as well. So if you had an equation like that, but they'll obviously get more complex than this. If you had like log base 21 of 3x minus 4 equals log base 21 of x plus 12. We don't really know what x is just like going into this. Like we're really not sure, but we can say for sure that those arguments, they really have to equal each other. There's no conversational way around that fact that the things in parentheses have to equal each other. So if this is a true statement, then we can jump out of this statement and say, oh, so then 3x minus 4 has to equal x plus 12. It's a fact. Got it? Sometimes you'll hear me use the expression, people just drop the logs, like, and some people laugh at that, but like you can just drop off the logs because it's just, they essentially become purposeless if they have the same base. You just set the arguments equal to each other. And usually what happens is you kind of look at it and you say, this one with the blue star next to it, that's a high school math problem. And then immediately, as you've seen before, this one with the white star next to it is like a little baby kitty equation, right? It happens quickly. So that's kind of the introductory phase of this. Those are the three things you need to know in order to get through the problems for the day. Good? Okay. So I don't know how many of these, I remember when I wrote them that each one I felt had a purpose. So let's start cranking them out and see how we do. So for our first problem, we have log base 19 of x squared is going to be equal to log base 19 of 12 minus x. You come to really appreciate these problems. There's no properties really. It's a property, but I mean, you don't have to condense or do anything fancy. If log base 19 of blah equals log base 19 of blee, then I think if you've been here for the last 5 minutes, you would agree that blah has to equal blee, right? So in a case like this, we can literally just drop the logs. What would our equation say? Very good. And in yet another new sort of twist, you'll see now today that our logarithmic equations are going to produce quadratic equations, which for us by this point in the year is like, I got this. So now that it pops out, this is not a little kitty 7th grade equation, right? It's a quadratic. How would I solve this quadratic? Yeah, let's just move all the stuff to the left because that's where big granddaddy x squared says like, hey, everybody come over here. Party at my house. So x squared plus x minus 12, of course, equals 0. And then we have to factor. And what would plus x minus 12 factor into?
Plus 4 and minus.
Absolutely. So our solutions, or so we claim at this point, are, I'll write them over here in, I'll do different colors. We have x equals 4. And we have, excuse me, we have x equals -4. My apologies. X equals -4. And then, of course, we have x equals 3. So in a new twist today, you do now need to start. You will just miss a lot of problems if you don't. You need to start checking your answers. And one of the things we're going to see is you can have a number that doesn't work if either the left and the right sides just out in the open don't match. Like if this side says log base 4 of 10 and this side says log base 4 of 11, you're like, well, those aren't the same. But another thing that can happen is you need to think about that the argument of a log can't be a negative number. And I said that so casually, and I know that only probably 4 of you heard that, so I'm going to say it again. The argument of a log cannot be a negative number for reasons. I mean, I think it should probably just, you should probably just make sense of this. Like if I gave you log base 4 of -16, can we all agree that that is, I'm going to use the L word again, literally impossible? Could you ever raise 4 to some power and have it come out to be a -16? impossible. You can do a lot of things with 4. You can make it bigger, you can make it into a fraction, but you sure as daylight can't make it into a negative number. So the main red flag that we're going to look for is when the arguments of our logs go negative, then we can say right away, you can't work. You can't be a solution because you've created badness in the problem. So you will see left, right not equal each other, but most commonly you'll just see a negative argument. So let's take these for a spin. So I'm going to test out my red number first, x equals -4. If you put -4 right there where that red circle is, what's -4 squared? So you would have log base 19 of 16 on the left side. And then if you put -4 right here where this other red circle is, what would that one become? Another 16, good basics, 12 minus -4, 12 plus 4, 16. Log base 19 is 16. I don't know what it equals, but I know it equals log base 19 is 16. So because those equal each other and there's no negative arguments, we can say x equals -4. You're a good solution. So I'm going to erase some of my work and I'm going to box that one up. We're back to that idea of let's box up what works and let's cross out what doesn't. So I like 4, I like -4. Let's test 3. If you put a 3 in place of this x, what's 3 squared? So you get log base 19 of 9. And if you do it on the right-hand side, what's 12 minus 3? It works again. So this is an example of a problem where we got 2 solutions and they both work. So I would present both of these answers with boxes as if to say they both work. Good. Okay, let's head on to the next one. For this one, and I'm going to stick with the same property for just a little while here. The first 10 minutes of my notes or so are just all hitting this drop the log sort of property. So this time we're going to have log base 14 of 6 minus 3x. And we're going to set that equal to another, of course, log base 14. And this time it's going to be of x squared minus 2x. So what has to be true if this is true? Of course, right? We could just drop the logs in a case like this, and then out pops a little sort of algebra 1-y equation, a little baby quadratic. Let's move all the stuff this time to the right. So we would have x squared, and then how many x's? Well, if we add 3, but we only have +1 now, right? Because we already had -2. And then what else? -6, set it equal to 0. And of course, factor, what do you get? Nice job. +3 minus 2, resulting in the answers x equals -3 and x equals +2. So I'll leave myself a little bit more room this time. So I'm not boxing them yet, and I'm not crossing them yet. They're still in that math sort of limbo state where we don't know, are you good or are you bad? So to test them, we're going to go and let's follow the red circles first. We're going to put -3 right there first. What's that going to equal? Yeah, 6 plus 9. Is everybody okay with that? Just some basics. So that's log base 14 of 15. And now just kind of fingers crossed that when I put it in on the right-hand side, that the same thing will happen. So this time, if we change both of our red x's into -3s, what's -3 squared? 9. And I think that's another +6, which last I checked makes 15. I think x equals -3 can have himself a box. Right away here, you're going to see something that I didn't mention, but I'm glad it's popping up in this example. This is going to be a real quick check. You don't have to proceed with the entire process. If you find badness right away, stop. If you find something that can't exist right away, something that's undefined right away, just stop. So this 2, all I need to say is let's put it right there in that blue circle up at the top. What is 6 minus 3 times 2? I forgot to say this, the log also cannot have an argument of 0. Therefore, x equals 2 can't work because it creates something that doesn't even exist. So for that reason, x equals 2 is going to get across. And I would explain it to you the same way. Like if I asked you to figure out log base 14 of 0, again, I'm sorry to be this guy, Mr. Bossy over here, but there is literally no power that you can raise 14 to turn it into a 0, right? You try for a million years. What is 14 to the 0th power? 1. Like I'm screwed. I cannot make 14 into a 0, and I certainly can't make it into a negative. So if the argument of your log comes out to 0, or if it comes out to a negative, then you've found badness. Cross it out. Move on your way. Don't even care what happens on the right side. Good. They would equal each other. You could make a case that they equal each other, but since neither of them exists, then 2 is not a valid solution. Like they both come out to log 14 of 0, but it doesn't work. Right. Okay. No. In fact, you wouldn't even have log with like a base of 1 because it would just be redundant, like everything. You know what I mean? I don't even know if redundant's the right word. It would only work at 1 point, right? 1, I believe. 1 to any power is 1. So, no. Are we good so far? All right, let's try this one. Log base 5 of negative 13x equals log base 5 of negative 30 minus x squared. Drop the logs, right? What do you get? Right. So just get used to this. Not all of your problems are going to be quadratics. I just thought I would focus this lesson on the quadratics since they're undoubtedly more difficult. So let's pull all of our stuff this time to the left because I want to change my x squared into a positive guy. So I'm moving x squared to the west, making him positive x squared. I'm leaving Mr. minus 13x where he's at, and I'm going to add the 30 across like this. Leaving us with what at this point should be a relatively simple factoring situation. X minus 10, x minus 3 is perfecto. So my answers at this point are x equals 10. My answer candidates, I should say, and x equals 3. So let's test 10 real quick. If you put 10 in place of x right here, what's the argument of your log become? And as we've said before, the log cannot have a 0 or negative argument. Therefore, 10 right out of the gate. Don't even have to do any math. It just can't work. And I believe you'll see that the same thing happens if you test the 3. If you put 3 now where the blue circle's at, what is negative 13 times 3? It also doesn't work. What would we say? No solution. You've seen this before. If you get candidates and none of them work, well, I guess no one's going to work. That's that. I don't know. And the last thing I wanted to do before we get to the second side of my note card is talk about the other type of log, because I know that it's going to come up. If I had like the natural log of negative 13x minus 3 equals the natural log of negative 4x plus 6. Again, you don't see a base, right? But you do know that these are matching logs. What are they? Log base what? E. Very good. So these are base E logs, which in this case doesn't matter. They're the same logs. We can drop them off. So this time what pops out is a little 7th grade equation. You just get argument of the left side equals argument of the right side. And then do a little bit of basic algebra. You should get 9x over here. You should get negative 9 over here. You should make the claim that x can only equal negative 1. So let's take negative 1 for a spin and see how it goes. So if you put negative 1 where the red circle's at, What's negative 13 times negative 1? 13 minus 3. So you get natural log of 10 on the left. And if you put negative 1 in place of this other red circle, you get 4 plus 6, which again is natural log of 10. Last I checked, I don't care what the natural log of 10 is. It's 2 point something. But I don't care. I just know that the natural log of 10 equals the natural log of 10. So those are good to go. Any questions on that first portion? Okay. On to the second side. And don't worry, you'll have lots of time in class tomorrow as well. We've done this before. So today hopefully I can wrap this up in 10 minutes or so, and then you'll get some time, but then tomorrow you'll get a bunch more time. So on this side of the page, we're going to have to use that condensing property, or those condensing properties where we take two logs and mash them into one. So for our first one, we have log base 3 of 6 plus log base 3 of the quantity x plus 8 equals 1. So this is going to now feel like a hybrid. This is going to go, you're going to start to see now a lot of properties and things you've talked about with logs sort of all gelling into, sometimes just one problem sees 2 or 3 different properties of logs. So tell me about this left side. Over here, what can I do, or should I, or need I do? Yeah, you need to condense the left side. You must condense it into a single logarithm so that we can do what we're about to want to do. So the left side is going to condense into a single log base 3 of 6x plus 48. So that's just multiplying the arguments of the logs together. That was our very first property of the day. And this should now look familiar. This is not a drop the log problem. You cannot drop the logs because there's not a log on the right-hand side. So this is where we do what we did last week, and we embrace the water cycle diagram. So we say this to the this equals this. Hopefully that looks familiar. What would my equation then say? Well done. And then, of course, you got a little baby equation to solve. You're going to wind up with 6x equals negative 45. And this probably is a good time to utilize your calculator just to give us a decimal approximation. I don't know exactly what it is, but I can say it's going to be negative. And 45 divided by 6 is 15 divided by 2. I should be negative 7.5. So you're not allowed to say that can't work because it's negative, right? I can't say that. What I can say is I have to check it and see if the argument of the logs themselves become negative. So I'm going to go back to the very beginning of the problem, and I'm going to test negative 7.5. And there's only one logarithm I have to test. So follow this little blue circle right here. Good, good. And honestly, I've not seen many, if any, examples of when the math itself doesn't check out. What I'm primarily concerned with is this. If you put negative 7.5 right there, what is negative 7.5 plus 8? Nice. And so you could say that that logarithm with the blue arrow pointing to it is log base 3 of 0.5. And since it's not 0 and it's not a negative, it's okay. And if you want to take it a step further, you can, check it all out, put it in a calculator, but this will work just fine. Okay. But if you want to check it, that's going to be a little tricky. Have we talked about the log button on your calculators yet? Okay. So why don't we, for today, let's just go with this today until I show you, because I don't want to do it today. I don't want to overwhelm you with that stuff. Today, just assume if you don't get a negative or a 0 argument on a log, that you're good to go. So I would call negative 7.5 a good solution. Okay. Let's do a division problem. So that one would get a box. So let's do log base 6 of negative 4x minus log base 6 of 7 equals 1. What's he doing over there? Homie takes good notes. Spaces them out. So we're going to have to do some condensing over here on the left. I know this is starting to, I've dragged well past the point when the studies show that kids are able to listen, but you gotta hang in there. So we got to condense the left side. What's it going to become? Nice. Equals 1. And again, I can't drop the logs on a problem like this just because it's not a log on the right side. What's my next equation going to say? Good job. 6 equals negative 4x over 7. That's the water cycle base to the log equals argument. So let's talk about way back in time. How do you solve an equation like this? Yeah, you got to multiply both sides by 7. And so we wind up with 42 equals negative 4x. And then, of course, we divide both sides by negative 4, which gives us x equals, is that 21 over 2, so negative 10.5. Good. So I have to know, does it work? Like, does it break any laws? That's really, I guess, what I should be saying is. So let's take negative 10.5 and put it back up in the original problem. So if you put negative 10.5 where that red circle is, what do you get? Positive 42, right? And that's good. So good to go there. So again, only go so far as to say, does the logarithm have a negative or a 0 argument? If it doesn't, then we're good to go. You guys good? I think I'll just maybe pick one more of these. I feel like I've overkilled it here, so let's do one more. Log base 9 of x minus 4 minus log base 9 of x equals 3. So we're going to condense. Are we going to use the times condense or the divide condense? The divide condense. Very good. So it's going to condense into a single logarithm with a base of 9. And what will the argument be? Very good. No. No. Let me see if I can find something for you. We'll talk more about this when we get to rational expressions, but one of the most common errors people make is trying to cancel out things that are parts of addition problems. So Mrs. Eklund and I discovered this meme, I guess you'd call this, and it kind of just puts in perspective, unless you're some sort of psychopath that likes murdering kittens. When something is part of a plus or a minus, it's not cancelable. And that, again, is a conversation for some other day. But just know that in the problem, yeah, look at the little kitten. Every time we cancel out something that's part of plus or minus, that kitten dies, or someone who looks just like him. Clear? Okay, good. So in a case like this, no, 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 with a capital N and a side order of no, and to drink a nice frothy glass of no, and for dessert, some little no puffs. No, 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 do not cancel those X's. So having said that, let's do the water cycle diagram. What do we get? 729 equals x minus 4 over x. That's 9 to the third power, right? How are we going to solve this? Multiply both sides by x. Very good. So that's going to go x over there, x over there. X's are going to cancel. We have a mess. It's okay. So we have 729x equals x minus 4. Keep on keeping on. How do we solve? Now, I would subtract this x across. Get 728x equals -4. And now what do? You divide by 728, and you wind up with x equals, this is well outside my comfort zone, 4 divided by 728. I don't want a fraction, but I appreciate that. So I have negative, and I should change this to the squiggly equals. It's negative 0.0055. That should be enough accuracy. So again, my only concern at this point in time is that going to make something bad happen? I mean, that'll be enough information to tell me if I'm going to break any laws. So if we take negative 0.0055 and go back and put it up in here, if you were to put a negative number in either of those green arrows, what would you surmise? There's going to be a log of a negative. And I don't even care what it equals. I just know what's coming down the pike. You can't have log of a negative. So that being the only candidate I had for answerdom, he says, I don't work. You say, well, then there is no solution. You're going to find this worksheet to be challenging only in one sense, and that is that there's a lot of problems mixed together. So there's lots of different flavors now coming at you. And this will be a good test for you over the next couple of days to see, can I shift from one mode to the other, to the other, to the other? So I expect a lot of questions. That's okay. All right. Cool. All right. This real quick. Let's leave our answers as fractions, except let's convert them to decimals. Thank you, Kevin. Let's convert them to decimals, though, only for the practical purpose of checking. But when we go to express an answer, let's leave it as a fraction. So like on problem number 1, you all should have dropped the log and very quickly arrived at the conclusion that 5x has to equal 2x plus 9, right? So that's just a simple drop the log problem. Those are both log-based 10s, so they just fall off. And then I would subtract the 2x and get 3x equals 9. I would divide by 3 and get x equals 3. So this isn't one where decimals even pop up, right? So let's head to number 3. So anyways, if you check 3, you can see you're not going to encounter any issues in problem 1. So 3 can have a box. So let's jump ahead to problem number 3, because this is where the decimal fraction sort of situation comes up. So problem 3 is another drop the log problem. Base 10 doesn't matter. I mean, they're the same. So if you drop off the logs, you wind up with 4p minus 2 is going to be equal to negative 5p plus 5. So again, we're just faced with linear equations, little 8th grade equations here. So add your 5p across, you get 9p. Add your 2 across, you get 7. And here you have an answer of p equals 7/9. Now, for the sake, if you wanted to get in there and use accuracy, you could take 7/9 and convert it to 0.7 repeating. But I think that I would look at it and say, okay, if you put 4 in your calculator times 7/9, some of you might struggle with that. So you could, for the sake of checking it, you could call it around 0.7778, right? Because that's what 7/9 is, a buttload of 7s. So when you go to plug it in, but I mean, if you're a math person, just think common sense. Like if you do 4 times that number, it has to be bigger than 2 because it's bigger than a half. But if you're not that kind of person who thinks that way, then just turn it into a decimal, plug it into the argument on the left, plug it into the argument on the right, and then if neither of them comes out negative, you're good to go. But as far as the answer is concerned, does it work, by the way? Sorry, I didn't mean to interrupt all your hard work there. So if I do like on the left, I get a positive argument, I'm good to go. If I do it on the right, I get -5 times 0.77. Since no one was talking to me, I just decided to do it by myself. They don't equal each other?
What equals?
That's not even possible.
I ran through it, I got, they both.
They should, yeah, you're really freaking me out. They both have to equal each other. I mean, if you think about the core idea, yeah, this works. Anyways, if this is true, then they have to equal each other, or our skills of solving equations are a little sus. But anyways, it does work. Check it again if you want. But I would box this as my answer. Remember, this was just a utility. It was just something that I converted to. But if you know how to do fractions on a calculator, then maybe the whole idea of a decimal will just never come up for you. You know, we've done this before. What's the matter? Fair enough. Sage, you okay?